Okay, so now that we understand the composition of these Jordan blocks, here is the main result. It says that any matrix A can be written as A equal to P J P inverse, where P is an n cross n invertible matrix, of course, and J is the Jordan canonical form of A. Okay, so Jordan canonical form of A, and it's written J is equal to, it's basically a block diagonal matrix with all the blocks corresponding to, with all the diagonal blocks will be Jordan blocks, J and K, lambda K. Okay, so that's what's very interesting about this. Okay, so it tries to write any matrix A. So any matrix meaning any square matrix here, not necessarily symmetric. Any square matrix A, it writes it as some matrix P, J P inverse, where J is a block diagonal matrix. Okay, it's not a diagonal anymore, it's block diagonal. Okay, if you were symmetric, you would have gotten diagonal, right? And you would have gotten a transpose here, and you would have gotten that the columns of P are orthogonal. All those are missing now, right? P is just some arbitrary invertible matrix, right? And J is the Jordan canonical form of A. Okay, so when we say the Jordan canonical form of A, also implies that this decomposition is unique. Okay, this decomposition here is unique decomposition up to permutations. Okay, up to permutations, meaning that I could potentially change the order in which I write the columns of P. Okay, that would result in a corresponding permutation of J. Just like when you have a symmetric matrix, you can write the eigenvectors in a different order. That will give you a slightly different decomposition in which the eigenvalues are also written in the correspondingly different order. Right? Same thing here. Okay, other than that, there is no non-uniqueness issue. Right? This decomposition is actually unique. These sizes in particular are very unique. Okay, these sizes are very, very closely related to the algebraic and geometric multiplicities of the corresponding eigenvalues. As I told you, if you take all the sizes, the sum of the sizes of any eigenvalue, sum of sizes of all the Jordan blocks corresponding to any eigenvalue, you will get its algebraic multiplicity, right? And the number of Jordan blocks corresponding to any eigenvalue is its geometric multiplicity. Okay, so that is the main idea here. Okay, and of course n here is going to be equal to summation of ni. Okay, I equal to 1 to k, sum of all these sizes. Okay, so that's the Jordan that's the Jordan canonical form. It's an extremely powerful result that actually tells you how to write an arbitrary matrix in terms of block diagonal matrices. Okay, let's try to understand this a bit better. So look at symmetric matrices. A similar result is A equal to VD V transpose. Okay, which can also be written as VD V inverse because V is orthogonal, right? So it's very similar to that here, right? For symmetric matrices, we understand the columns of V are the eigenvectors, right? And you get that just by writing AV equal to VD, right? You write the same thing as AV equal to VD, correct? And then you look at it column wise, you will get that the columns of V are the eigenvectors. So let's try to do the same thing here, right? So I'm going to write the columns of P in a special way. You will see in a minute, right? So suppose P is like this. Okay, it's got columns like this, right? So the first column here I'm going to write as P11, P12, so on, P1, N1. Okay. So these are the N1. So these are the columns of P. Let me write corresponding to block 1. Okay, corresponding to block 1. So block 1 is of size n1. So let us say that these P columns correspond to that block. Okay, and then let me write P2 1, P2 2, P2 N2. Okay, these are the columns for block 2. Okay, and similarly columns for block 3. Okay, so in general Pij, okay, so I denotes the block index, so the ith block, and J denotes the within that block. Okay, so jth vector in block I. Okay, so that's how I'm going to write the columns of this matrix P. We'll see in a minute why it's useful. Okay, so let me start from here and write AP is equal to JP, AP equal to PJ. Okay, AP equal to PJ. Okay, fine. So here from this you will see that P11, P21, P31, so on up to Pk1, okay, are the k eigenvectors, okay, k linearly independent eigenvectors, I mean k linearly independent eigenvectors of the matrix A. Okay, so if you know the Jordan canonical form, this decomposition like this, you can simply read off the eigenvectors. Not all columns of P will be the eigenvectors. Okay, of course, because you know, right, if matrix is symmetric, it may not have any eigenvectors. Okay, so doesn't have any eigenvectors. It has k eigenvectors. The number of eigenvectors will be equal to the number of Jordan blocks as discussed earlier, right? And the first column corresponding to each block will be the eigenvector of that matrix. Okay, so the first column in block 1 is P11, the first column in block 2 is P21, similarly first column in block 3 is P31, so on. These are the k eigenvectors of A, right? This corresponds to eigenvalue lambda 1, this corresponds to eigenvalue lambda 2, and so on. This corresponds to eigenvalue lambda 2. As I discussed before, many of them may be similar, right? So lambda 1 and lambda 2 may be equal to 1, as in an example discussed earlier, in which case these two will be the eigenvectors corresponding to eigenvalue 1. Okay, so on. So this gives you directly how do you find the eigenvectors of the matrix. Okay, fine. Now this tells you what these columns are. Okay, what these columns are. But what about the remaining columns? For example, what about, let's say this column over here. Okay, so what that column is you can think about that column in terms of the difference. Okay, so let's say I look at A minus lambda 1i. Okay, A minus lambda 1i. So we can actually argue that A minus lambda 1i, if you go by this decomposition, is actually P times Jn 1 lambda 1 minus lambda 1i, Jn2 lambda 2 minus lambda 1i, and so on. Okay, Jnk lambda k minus lambda ki. Okay, so what happens is, what's happening here is basically times P inverse, sorry. Okay, what's happening here is that when you subtract an identity matrix, it will just go ahead and subtract identity from everything here. Okay, that's what will happen. Okay, so what that means is that P12 is in the null space of A minus lambda 1i whole square. Okay, A minus lambda 1i whole square. So if you look at the null space of A minus lambda 1i whole square, it will have both of these vectors. It will have P11 and P12. P11 will already be there because A minus lambda 1i times P11 is 0. Right? It's an eigenvector, correct? P12 will also be there when you take the square, similar to how we discussed before, right? So if you take P13, that will be is in the null space of A minus lambda 1i whole cube. Okay, in fact you can go ahead and construct this chain. So what you can do is you can look at these vectors here and you can construct a chain like this, right? P1 n1 to P1 n1 minus 1 to P1 n1 minus 2, so on up to P11 to 0. Okay, so you can construct this chain here, and what it means is that if you apply A minus lambda 1i, okay, to any element of this chain, it will take you to the next or the successor element in that chain. Okay, meaning if you apply a minus lambda 1 I here to this vector, you will get this vector. If you apply it to this vector, you will get this vector, and if you apply finally to this, you will get 0. Okay, so this is actually a Jordan chain corresponding to this matrix A. Similarly, these columns will form another Jordan chain. Okay, so if you can write down the Jordan chain corresponding to that, you will get P2N2 minus 1, P2N2 minus 2, so on, P2, 0. Okay, so here what will happen is, in this chain, if you apply a minus lambda 2I to any element of this chain, so remember the operator is different here, right? Here you apply a minus lambda 1I, a minus lambda 2I to any element of the chain, you will jump to the successive element in that chain. Okay, so applying a minus lambda 2I here will give you this, applying this here will give you this, and so on and so forth. Okay, so what this also gives you is a very nice way to find out vectors in the null space of certain differences. So let's take an example. Suppose my matrix A is like this. Okay, the example I discussed before, J10 J5 and J20 Okay, I discussed before 1 and 3 are the eigenvalues, right? 1 has an algebraic multiplicity of 15, 3 has an algebraic multiplicity of 20, 1 has a geometric multiplicity of 2, 3 has a geometric multiplicity of 1. Okay, that is what is happening in this matrix, right? So here I haven't put the piece, just for simplicity. You can also put the piece, nothing much will change there, right? So if somebody asks me what is the null space of a minus 3I whole to the, let's say, square. Okay, what is the null space of a minus 3I whole square? Okay, what will you get? Okay, what is the null space of a minus 3I, by the way? Right, what is the null space of a minus 3I? We discussed this before. This is the eigenvector corresponding to 3. Okay, so you have to look at the column corresponding to this block. The first column corresponding to this block, which we discussed before, was E16. Okay, so in the null space of this matrix, you only have E16. Okay, and its multiples. So E16 is the only unit vector in the null space. What about a minus 3I whole square? Right. So here the vectors will be E16 and E17. The first and the second columns corresponding to this block. Okay, so here it's as if you had a equal to, so let me just clarify it a bit more, I times this times I inverse. Okay, so I is your P here, correct? So in that context is what I am reading, right? So E16 and E17 both are in the null space of a minus 3I whole square. Okay, what about a minus 3I whole cube? How many vectors are there in the null space? Well, E16, E17 and E18. These are the vectors in the null space of this, right? So in fact, you can readily say the nullity of this is equal to 3. The nullity of this is equal to 3. And the nullity of this matrix is equal to 2. The nullity of this matrix is equal to 1. Okay, actually gives you quite a lot of information in that sense, right? What about a minus 3I whole to the power of 20? What is this going to be? How many vectors are there in the null space? Well, it's all the way from E16, E17 up to E35. Okay, so the nullity will be 20 from this matrix. Okay, fine. Similarly, so this was for a minus 3I. I looked at this eigenvalue 3 and I subtracted it. But what if I take something that's not an eigenvalue? What of a minus 5I? Is there any vector in the null space of a minus 5I? There is no vector in the null space of a minus 5I because 5 is not an eigenvalue, correct? So the nullity of this will be 0. Okay, fine. Similarly for the squares, okay, if a minus 5I has nullity 0, a minus 5I whole square will also have nullity 0. Okay, because because a minus 5I is invertible basically, correct? So this sort of thing makes sense only when you pick this number here, whatever it is, to be an eigenvalue, right? You don't just pick. So I don't have to consider a minus 5I, a minus 10I or all those things, right? I only need to consider a minus 3I and a minus I if I am interested in the null space, because everything else will be invertible, right? So what about, so let me rewrite that matrix here for reference. J10 1, J5 1 and J23, right? What about the null space of A minus I? How many vectors are there in the null space of A minus I? Well, null space of A minus I means eigenvector of 1 corresponding to eigenvalue 1, eigenvector corresponding to eigenvalue 1. So there are two eigenvectors, one from each block, right? So this null space has E1 and E11 as we discussed previously, E1 and E11, correct? So that's the first eigenvector of this block and the first vector of this block and the first vector of this block, okay? And yeah, so the nullity is 2, right? What about A minus I whole square? How many vectors are there in A minus I whole square? Okay, so that will be, well, you will take the first two vectors of each of these blocks, okay? So that will be E1, E2 and E11 equal. Nullity will actually be 4. Okay, so what about A minus I whole cube? We will take the first three vectors from each of these blocks, okay? So that will be E1, E2, E3 and E11 equal E13. Nullity will be 6. Okay, okay, let's just keep going. What about A minus I whole to the 6? Okay, well, you might want to pick 6 from here and 6 from here, right? But this only has size 5, you cannot pick 6, right? It's going to be E1, E2, E3, E4, E5, E6, but you'll only do E11 equal E13, E14 and E15. I cannot go beyond that, right? So it's not going to be 12 here, it's going to be 11 in nullity, because there are 11 vectors here. Okay, okay. So you can find the nullities and the null spaces of any of these matrices of the form A minus lambda I, okay, using the Jordan form very easily. Okay, right. For example, what if I ask you what is A minus let's say lambda 1I to the power of so we just do it this way. What if I take A minus lambda I, okay, whole to the power of the largest value of the nk. Okay, fine. So I'll take the largest. For example, here in this scenario, I'll take A minus lambda I to the power of 20, whatever is the largest number, right? So what will you get, right? If lambda is not an eigenvalue, then this matrix is an invertible matrix, right, as we discussed before, correct? But if lambda is an eigenvalue, let's say lambda is 3, right, then A minus 3I to the 20, we already know that it has a nullity of 20. We discussed that before, correct? But what if I have A minus I to the power of 20? What will that have nullity? How much will that nullity be? A minus I. So if lambda is 1, A minus I to the 20, what will be the nullity? I have to take the first 20 from here and the first 20 from here. But I can't take 20 because 20 is too big. So I have to take 10 from here and 5 from here, right? So the nullity of this in some sense is going to be simply the algebraic multiplicity of lambda. Okay, algebraic multiplicity of lambda. Okay, so in this case also the answer will be just the algebraic multiplicity of lambda. Okay, fine. So I will stop here. So this lecture was a bit light on proofs, but that's the intention. The proofs are a bit complicated and beyond the scope of this course. But it's very interesting that arbitrary matrices, not just symmetric, have this wonderful decomposition in terms of the Jordan canonical form, and the block sizes of the Jordan canonical form give important information about how many eigenvectors there are, about the geometric multiplicities, and the corresponding P also gives some very important information about the null spaces. Okay, by the way, the columns of P are called the generalized eigenvectors. Okay, so I'll just write that down. The columns of P are called the generalized eigenvectors. So they are not eigenvectors. Not all of them are eigenvectors, right? Only k of them are eigenvectors, right? Out of n, only k are actual eigenvectors. The remaining ones also you'll call them generalized eigenvectors. Okay, fine. In spite of all these wonderful properties, the Jordan form remains primarily a theoretical tool. For proofs. For example, I mentioned earlier that if the spectral radius is less than 1, then the matrix powers converge, right? To prove things like that, you use Jordan form, but computationally, a Jordan decomposition like this is very unstable. Okay, so let me just rewrite it here. So you have A equal to P J P inverse, right? This Jordan decomposition I said is unique, right? That's all well and good, but we also expect, in addition to uniqueness, we expect stability. What does the stability mean? Meaning that suppose if the entries of A are slightly changed, you don't want the Jordan form to change a lot. Okay, but unfortunately that's what does happen. For example, let's take this example which is there on Wikipedia, and I think it's a very good example. So suppose if you have this matrix 1 1 0, sorry 1 1 1 0. Okay, this is not a symmetric matrix. In fact, it's already in its Jordan form, correct? Because this is J 2 1, correct? This is the Jordan block of size 2 corresponding to 1, correct? So it's already in its Jordan form. Okay, so it's very easy to find the Jordan form of this, and this is what it is. But suppose I change this entry over here slightly. Okay, so I make this epsilon 1 1 epsilon 1. Okay, so I make this entry to epsilon, very small perturbation, and not change by much. Epsilon could be like 10 to the minus 10 or whatever. Okay, very small change. Then what happens? It's no longer a Jordan form now, is it? It's no longer a Jordan form. So to make it, let's try to find its Jordan form, right? So to find its Jordan form, without doing much, let's just try to find its eigenvalues first. Okay. And what are the eigenvalues of this matrix, right? So you can see that the sum of the eigenvalues is 2, that is a trace, and the product of eigenvalues is 1 minus epsilon. Okay. So the eigenvalues can be seen to be 1 minus square root epsilon and 1 plus square root epsilon. These are the eigenvalues, correct? 1 minus square root epsilon, 1 plus square root epsilon. Okay? And these eigenvalues are distinct, correct? If epsilon is non-zero, the eigenvalues are distinct. So in fact, the Jordan form can readily be written to be 1 minus square root epsilon 0 0 1 plus square root epsilon, correct? Because if the eigenvalues are distinct, correct, each eigenvalue has algebraic multiplicity 1. There should be only one block corresponding to each eigenvalue. Okay, so that's what you will get, 1 minus square root epsilon 1 plus square root epsilon. You can see that the Jordan form has changed significantly, right? This is the original Jordan form. This is the original Jordan form, and this is the new Jordan form obtained by perturbing slightly. You see that they're vastly different. In fact, it's the involvement of square root epsilon makes it also pretty bad. Okay, because epsilon is, let's say, 10 to the minus 10, then square root epsilon will be like 10 to the minus 5. Okay, so you can see that the change here is much more, right? I mean, it's 10 to the minus 5 is much bigger than 10 to the minus 10, right? Order of 10 to the 5 bigger, correct? So it's not stable. Jordan decomposition is not stable and not used numerically. So algorithmically, you'll not use it to find things, find eigenvectors or things like that. Okay, there are other methods for it which we cannot go into detail, but it's really useful theoretical tool and also for understanding conceptually, right? Understanding about these geometric and algebraic multiplicities, the Jordan decomposition gives a wonderful tool for you to accomplish that.